Hi everyone, it's Mr. H here, and today we're going to talk about concave and convex mirrors. You've probably seen in a spoon before, and if you haven't, go grab a shiny one and look at both sides of it. You'll see that on one side, with the convex side is what we call that, this one here, where the spoon is kind of bubbled out towards you, you're actually going to look a little bit smaller, but you're going to look upright. But you'll notice that if you turn the spoon around to the concave side, this one here, what you're going to see is you're going to see yourself, if you're some distance away, as upside down. If you bring that spoon really, really close to your face, if depending on the curvature of it, you should be able to see yourself, again, become right side up and bigger. And so what we're going to get at in this lesson is really why this all happens and how it works. So here we go. Before we actually draw the ray diagrams, it's important for us just to understand a few key terms. Now you'll notice here this is a concave mirror on the left, and so that concave mirror has lines on the back, and those lines represent the back of the mirror. And so the object is always placed in the front, and we have that object sitting on this horizontal line. That horizontal line is called the principal axis. And then that principal axis, on that principal axis, is the focal. That focal point is important because the focal point is, if we have any parallel lines that come in parallel to that principal axis, what they're going to do from that mirror is they're going to reflect off through that focal point. So if any other lines down here, anywhere coming in, it's going to reflect back through that focal point as such. And so that's the beauty of the focal point. That tells us where all the light is going to focus together and converge together. Well, I'm just going to get rid of those lines for a minute as we label this. F is the focal point, and we label it with a capital F. And then if you take that and you double that distance, that's the center of curvature. And the center of curvature, you may have guessed, is if we had drawn this curved mirror and made a whole circle all the way around, C would be smack in the middle of that circle. So that's the unique thing about the center of curvature. This point right here, we label with a V, and that is the vertex. And then the last thing I want to notice here is obviously the mirror is there. On the other side, we have a convex mirror, and you'll notice what's special about a convex mirror is that the focal point and center of curvature are actually behind the mirror. If you think about it, some people wonder, why can't it be in front? Well, think about it. That all depends on the curvature of the mirror. And because it's curving backwards in this case, the focal point and center of curvature have to be behind the mirror. So let's label the focal point F, center of curvature C, let's label the mirror, and then again, just as we had before, this is the vertex, which is labeled with a V, and this is the principal axis. So we're going to use the following steps to draw ray diagrams, and I'm going to walk through them one at a time. And so the first one is this: draw a ray from the top of the object parallel to the principal axis, reflect through F. So let's do that. So on this next slide, what we're doing is we're going to draw a ray that goes from the top of this object parallel to the principal axis and then reflects through F. And so there's my first ray. Obviously there are millions and millions of rays being reflected off this object at any given time, but we're focusing in on the first one, and then we're going to focus in on two others, and that's all we'll have to do to figure out where that image actually lies. So that's the first one. Let's go back and look at the rules for the second one. The second rule says draw a ray from the top of the object towards or through F, then it reflects parallel to the principal axis. And there you see that coming through the focal point, reflecting parallel to the principal axis. And so those two rays are going to meet right here, and that's where we're going to assume the top of the image is going to form. It's worth noting that you need to make sure you do this with a ruler, and you need to do it very accurately. And even still, if the curvature of the mirror isn't perfectly around C, you might not get all the points meeting at the same place. The first two should meet up fine, but the third one, we'll see if that meets up just as well. Step 3 says draw a ray from the top of the object through C, reflect it back through C. And it goes on to say that the image appears where the three reflected lines join. We're going to continue them as dotted lines behind the mirror if needed. That will be for another example. Let's do this last line now. And so you can see here, this is a case where the curvature of the mirror actually wasn't centered at C. And so this mirror is a little off. So what I've done for this last one, because you might look at it and say, well, how's it supposed to reflect off the mirror if the mirror doesn't reach all the way down here? For the purposes of the ray diagram, we're just going to extend that mirror out. There are lots and lots of rays that are going to come together to form this image. But these are the three we're drawing. Now you'll notice here, like I said, because that isn't perfectly centered around C, these three don't come together very well, but we're going to assume it's about that point right there, the closest average of those 3 points. They should be ideally on top of each other, but if not, then we're going to draw it there. And this will be the image that we're seeing. So what we can see is a few things about this image. The location is in front of the mirror. In front of the mirror. Having a lot of trouble with my pen today. Sorry, guys. In front of the mirror. We also know that the orientation is going to be inverted. It's upside down. Thirdly, the size is a bit smaller. And lastly, this is a real image because it forms with real light rays in front of the mirror. So you'll notice that my slide says that this is for an object beyond F. It actually is for an object beyond C. We're going to see what happens when it's between F and C in the next slide. So let's go ahead and apply the same thing now in the next case. So what I have here is that initial ray coming parallel to the principal axis, reflecting through F. Now we're going to draw the second ray. So that second ray is going through F and then reflecting off parallel to the principal axis. And so just from that, we should be able to imagine that our image is going to look something like this in this case. Not with that big line there, but something like that right there. And so really that last ray is just to check that. Apologize for all the jumps in the screen, but can't get my pen working properly here despite battery changes and everything. Anyway, if we go and draw the last one through C, you might ask, well, how am I supposed to draw that through C? Well, great question. The reason you're able to draw that through C is because you're not actually drawing it through C, you're just lining it up with C. So we're going to line it up with C and then have it reflect back towards C. You can see for that last line, I've extended my mirror, lined the ray up with the C and the top of the object, and it's reflecting back on itself, and it's meeting up with the other two reflected rays right there. So that's my image formed inverted and further away and larger. So let's fill in these details. Location, orientation, size, and type. Location, it is beyond C. We also know the orientation is inverted. The size is larger. And the type is, again, it's real. Because a real image is formed when the reflecting rays physically meet. So the next one, we're going to see a virtual image. So let's go ahead and try to draw that yourself, and then check when you're done drawing it. So I gave you a little hint before you started drawing this that said that it's going to be a virtual image. And so hopefully that helped you get enough information to realize that the rays are not going to meet in front of the mirror, as we've seen already. Just to go over how I've drawn these, I had one that was parallel to the principal axis and came off through the focal point. And then I drew the next ray coming through F. Well, it didn't actually pass through F. I just lined it up with F, just like I did in the last ray diagram. And then it reflects off parallel to the principal axis. And finally, that last one, I line it up with C. I draw it so it reflects back through C. Well, what do I do with those? Well, I draw these as dotted lines now, the reflected rays as dotted lines behind the mirror. Not the incident ray, but the reflected rays. And so if I take all these rays, draw them as dotted lines behind the mirror, what I see is that they all meet up approximately there. And when I draw that as the top of my image, what I can see is that I have a much larger image. This is the principle that's used in makeup mirrors. So if you're very close inside the focal point of a concave mirror, you actually see your face a lot larger than it is in reality. And that allows you to pick your zits or whatever you need to do in the mirror. Yuck. Anyway, the location is behind the mirror. The orientation is upright. The size is larger. And the type, this is a virtual image because we've had to take the reflected rays and trace those back behind the mirror to get this image. When the object's at C, I want you to go ahead and draw that yourself, and tomorrow's Minds On is actually going to be accompanying this diagram. So this will help you with that challenge. Now for concave real-life examples. we see a makeup mirror, as I already mentioned. We could also have something like a solar mirror that allows you to be able to cook something in the middle. Telescopes often use this. There's a little reflecting mirror that allows it to have the light converge for your eye to be able to see it. And then the principle of satellite dishes works the same way, that the little collector that's right here is the focal point and everything bounces off of that into that collector. Believe it or not, there is a giant bean in Chicago. And it's not just any bean, it is a reflecting beam. And this is a concave mirror. If you ever go to downtown Chicago, check it out. I think it's still there. And you can look at it, and it obviously distorts the way you're looking at the world around you. But you'll notice that from this picture, nobody is inverted. And then, regardless of how close or how far away you are, you're always going to be upright and you're always going to be smaller. So the location, orientation, size, and type for a convex mirror is very simple because it's always going to be the same. The focal point is found with all the parallel beams coming in. They're going to reflect off, and then you draw the dotted reflected beams behind the mirror, and that's the focal point. Drawing ray diagrams is very much the same as what we saw earlier, remembering now that the focal point and center of curvature are on the other side of the mirror. And so what you can see from these lines that were already drawn for us, we can see that the first one here is coming in parallel to the principal axis. It's reflecting through F. So we line our ruler up with F, and we have it reflecting off in this direction here. And then we take the reflected ray and we draw it as a dotted line behind the mirror. This is always going to be the case for convex mirrors. The next one is coming in like it's going to go through F, but then it hits the front of the mirror and reflects back off parallel to the principal axis. And we can see from where those two reflected lines join behind the mirror that we already know where the top of our image is going to be, but then we do the third one, lining it up with C. So this lines up with C, it bounces back off the mirror, we draw the dotted line behind the mirror, and we can see that that goes through the same point as the other two. Now that's going to be our image. And so here we can see the location is behind the mirror. And we can be more specific actually here. We could say it's not only behind the mirror, but it's actually inside F. It's inside the focal point. The orientation is smaller. The size is smaller. I don't know why I keep writing orientation is smaller. The orientation is upright. There we go. The size is smaller. And the type is virtual. They're always going to be virtual in this type of mirror. Always virtual. So go ahead and draw the next ray diagram, and then you can check your answer with what the next image is on the video. So you can see there I started by drawing the blue, then I drew the green, and then I drew the gray one, the one in the middle there. And then I continue the reflected rays behind the mirror, and the image is going to be formed right here. Just as we said in the last situation, it's always going to be inside F. It's always going to be upright. It's always going to be smaller. And it's always going to be virtual. And so those are the blanks there as well. And so they're in a slightly different order. It says images in convex mirrors are always behind the mirror. That means they're virtual. They're always upright. They're always inside the focal point. And they're smaller than the object appears. It may surprise you just to see all the places that we actually see convex mirrors as well. We see these in bus and car mirrors. The front of your bus, when you get on the bus, when you're not in quarantine, you have a curved mirror like that at the front of the bus. We also see on the car mirrors, it says objects in the mirror are closer than they appear. That's because they are very slightly convex mirrors. If you ever go across a border, you might have seen someone check under your car with this type of mirror. Again, a convex mirror that's on wheels, just to allow to be able to check under your car. Store security mirrors are really common for that. And then the front of an airplane that sends the radar back to the satellite dish is also considered a convex mirror because it's reflecting the light rays back to the concave mirror, which is the satellite dish. So there you go. There's some good examples of that, and good luck drawing those ray diagrams.